I'm going to, given the time, I'm just going to let the recorder keep moving. This was the only question I had written originally that I did last quarter. So I wrote 7 and 8 kind of off the cuff. So I'll just walk through them with you, if that's okay, just given the time of the day and I have my other constraints. So I kept everything the same, and I had some students they've come into me to office hours to talk about this particular question, like questions like this. And I completely brushed over a question or an equation in the textbook. It's not on the equation sheet. And anyway, I'll walk through this with you, and then I'll explain what I'm trying to say here. So the maximum speed of the pendulum bob, the A omega, like that we have for the mass in a spring, it's very easy to define the amplitude of a oscillating mass, whether it's vertical or whether it's horizontal. It's a linear dimension measured in meters. How do you define the amplitude of a pendulum? So I haven't talked about that, and how do you really define it? So you could define it as an angle. Certainly has a maximum angle of displacement. You could probably think of it having a maximum XY coordinate, so you could think of like the direct distance from its lowest point, but it would be a two-dimensional distance, so it's much more difficult. So I do not want you applying A omega as we have defined for linear objects to pendula. It doesn't work. But there is a relatively easy way to get to the max speed of a pendulum bob just by going back to 114 or any of your mechanics courses you've taken. And I'll do this over here on the right. And so let's say we have a pendulum bob of length, or pendulum, simple pendulum of length L, and it sort of oscillates. I'll sort of exaggerate the diagram so it's a little easier to see what I'm doing. But everything that actually the energy won't depend on the small angle approximation, so this energy should be fine. But I'm going to define this here as theta max. So the ball, hopefully what you can see here is that if this is at the maximum value over here, that's when the ball has its maximum the ball earth system has the maximum potential energy. So I'm going to define this height here as y equals 0. So the point where it has its lowest point, I'm going to call that where it has no potential. I can define y equals 0 to be anywhere. It's completely arbitrary. That's up to the person analyzing the problem. So then at this point up here, I'll call this a position y. So that means that the potential energy up here, so U max, is mgy. It has a positive amount of potential at this point, and as it falls towards the equilibrium position, it basically converts all that potential energy to kinetic energy, giving the ball the maximum speed as it goes through the lowest point. So I would like to define y here, this distance y, in terms of theta max and L. So what we can do here is, I need a couple different colors, and I've probably put that L in an awkward spot here, but I'll do this in red. So this distance here, because this is still the same string, so this is L over here. So we've got a right angle triangle in this particular spot here. Oh God, too many L looking things. I'll just go to old school here. 90 degrees. So in red pen, this distance would be L times cosine of theta max. Which means that the distance here in, I'm not sure what to call this color, maroon, is going to be the total length L minus the red piece. So the blue line is L, take away the red piece, I'm left with the maroon piece, which is how much the ball drops. Agreed? So this is L minus L cosine theta max, which I can just take out that L, and I have 1 minus cosine theta max. Any questions to that point? to go. All right. So I have U max is equal to K max. Still, that's still true for a pendulum. So assuming again no air resistance, no friction at the pivot point, all that potential energy is converted to kinetic energy. So I know that this U max here is mgy. The K max is 1/2 mv max squared. So because it's a pendulum and it's in free fall, this is not a function of m. So both the U and the K are linearly proportional to m. So if I double one, I double the other. So this V max is not going to depend. So remember, if we way back to 114, when something falls, its maximum speed does not depend on its mass. All objects fall at the same rate. But I have this y. So if I get this y in terms of L, we're good to go. So this y is now, the y value is equal to L 1 minus cosine theta. And this is equal to 1/2 mv max. Oops, don't need that m in there. Sorry, bring that line down here just to separate the diagram. So here we can see then I can write the V max is going to be equal to the square root 2 times G times L 1 minus cosine theta max. And that's the expression that I would use. There is an expression in the textbook. So V max from textbook gives it as the square root of GL theta max. So I haven't just got the time in the last few days to equate these. So that's what they're basically equating theta max to is the square root of 2 times 1 minus cosine theta max. And it might be a trig identity that I just haven't had the time to look up, or whether they're doing an approximation. Also, the one in blue, I can't dispute. It's basically straight up energy conversion. So, for this question, we just solved for L in the previous question, the 0.16 meters. So if somebody is willing to do this calculation for me, it doesn't matter whether the theta is in, it basically has to match your calculator mode. If you're doing cos of 8 degrees, make sure your calculator is in degrees. If your calculator is still in radian mode, make sure you convert 8 degrees to radians. But we're doing a trig function, trig here, just to find the red value, so it shouldn't matter. As long as your calculator matches the correct mode. Yeah? Alright, so that's what I would go with. If you're trying to find the max speed of the pendulum bob. And that makes sense. It should depend on theta max. The more that you pull the pendulum out to, the more energy, in a sense, you start with, more potential energy you start with. The L also makes sense in the sense that's the greater height it would have. Okay. Recording's still going, right? Yep.
Would that equation be something that we could use on the exam?
Yeah. It's the one in blue I have no problem with. I haven't yet figured out what the author has done to resolve it to this. It works out, I think, as long as you have this theta in rads, I think everything works. But they get very close. They begin to deviate. So I kind of did a plot of thetas, and they're actually not the same. So it sounds more like an approximation than it is a trig identity. This I can't dispute. Like the blue stuff is based on energy and basic trig. I just haven't yet figured out, and the author doesn't say why he did it in this fashion. But Other questions? Okay, I'll do 8, and that'll wrap up. Oh yeah. I'll do 8, and I'll wrap up the whole